So here's an example of two loudspeakers that emit 500 hertz of sound waves with an amplitude of 0.1 millimeters. So each speaker is emitting the same thing. Speaker 2 is 1 meter behind speaker 1, and the phase difference between the speakers is 90 degrees or pi over 2. What is the amplitude of the sound wave at a point 2 meters in front of speaker 1? Okay, so let's refer back to what I wrote earlier. This is the sound wave. This is the amplitude of that sound wave. Okay, so let me just write it down. The amplitude is 2a cosine of delta phi over 2. The amplitude is equal to 2a times the cosine of delta phi over 2. And a here is 2 millimeters, or 0.1 millimeters. 0.1 millimeters. Delta phi is equal to, if you remember, it was 2 pi over lambda delta x, and then plus delta phi 0, the phase difference between the two speakers. Let me make sure I have it correct. Yes, I do. So here is speaker 1, and speaker 1 emits waves like so, let's say, right? Speaker 2 is behind it. But what does it mean for them to differ? Before I draw speaker 2 behind it, I ask you, what does it mean for speaker 1 to differ by pi over 2 and be exactly the same? If they didn't differ at all, then they look like this. If they differ by pi over 2, then speaker 2 basically starts here. Let me draw this. And it starts at the maximum. They differ by pi over 2. And then it goes on, all right? So this would be a max, a min, and so on. So that's how they differ by pi over 2. Now, speaker 2, so that means this thing here is a pi over 2. Right? That's what it means. Delta x is, so for speaker 1, speaker 2 is behind it. This is speaker 2. So the delta x here is, how much is it? Delta x is, one of them is 1 meter behind. Yeah, so this one is 1 meter behind. So this is 1 meter. So that's delta x. Delta x. So they differ by a 1 meter. One of them is physically behind the other by 1 meter. So before I proceed, I need to calculate I need to calculate lambda here. This is a sound wave, so it has a definite speed. So we know that lambda times f will be the speed of the wave, and so lambda would be v over f. The speed of sound in air is 343 meters per second, and f, we're told, is 500 hertz. 500 hertz. So we get 343 over 500, and that gives me 0.686 meters. That is lambda. And now we're ready to calculate this amplitude. Actually, let's calculate delta phi first. So we get delta phi will be 2 pi divided by lambda, but lambda is 0.686 times delta x, which is 1 meter, and plus Phi 0. Don't plug in 90 degrees. We're working everything in radians, so pi over 2. And how much do we get? We get this, and then we have to divide 2 pi by it, so times 2 times 3.14, and then plus pi over 2. Hope I didn't make any mistakes. 10.73, I get 10.73 radians. That's the phase. And so the amplitude, we will have A will equal to 2. Since little a is in millimeters, I'm going to leave it as millimeters. 0.1, we'll leave it here, millimeters, times the cosine of delta phi divided by 2. Make sure you set your calculator to radians though. So 10.73 over 2. So let's take the cosine. So I have this number already. Let's divide it by 2. And then let's do cosine of that. And I'm in radians here, so that's good. And then times 2. And then times 0.1 millimeters. So I get 0.12 millimeters. 0.12 millimeters. 0.121, if you like. And I think that's what, yeah, that is what they have. So the interference is constructive because it's the overall amplitude is larger than the individual amplitudes. It's not completely constructive because if it were perfectly constructive, the total amplitude would be twice. It should be 0.2, right? You have two waves. If you put them perfectly on top of each other, you get a wave twice as high. That should have been 0.2 if it were perfectly constructed. But nevertheless, it's still constructive. It's partially constructive. If it were less than A, then it would have been partially destructive interference. And if it's exactly 0, that is totally destructive interference. Okay. And so in the next section, they talk about interference as it applies to light waves. I'm going to skip that section for now. Because I believe you will talk about it in the next, in around Physics 231. So I don't think there is much benefit in talking about it right now. I also want to talk about interference of waves in 2 dimensions, or maybe 3 dimensions, just in 2 and 3 dimensions. And so if you have a wave now, instead of just being in a one direction, imagine you have a wave like this, and it's emitting, or a source is emitting waves. So here is the source, and it's emitting waves. So when I draw a line, that's the peak of the wave, and when I draw another line here, that's another peak. Okay, that's the peak. And this is the crest of the wave. That's the crest. This is the crest, and then in between here, that's the trough, the bottom of the wave. So this is the top of the wave, and this is the minimum of the wave. So this line is this, and this point in between is this. Okay. And so let me draw another one here. Another one here. Let's draw another wave now. Here is another source, and maybe it is in a different color. So here is a crest. Here is a crest. Here is a crest. Here is another crest. In the book they have it nicer than mine. So now, when do you have constructive and when do you have destructive interference? You see, when this is a maximum and this one is a minimum, you get destructive. And when both of them are maximum, you get constructive interference. Look at here. This maximum meets this maximum. This one is high, and this one is also high, maximum. So that's a constructive interference. constructive interference, constructive interference, constructive interference, constructive interference. Now, when do we get destructive interference? Let me draw one more for this one here, in this blue one. Just draw it here. Okay, so that looks like a little bit nicer shape. So you will get constructive whenever you have high and high. They meet together. Now, it would be destructive when one of them is high and the other one is in the low. For example, let me draw it in red, destructive here, in red. So, for instance, this wave, the blue one, is a minimum there, but the black one is maximum, so they cancel. So this is destructive. In here, destructive, because the black one is maximum and the blue one is in the middle, so that's the minimum. Let's see, that's destructive there. And so on. You can locate them. In the book, they drew them kind of parallel to get a nicer picture than the one I did. You can check it out. But in general, let's say you have a source here and another maybe source, let's say it's here, and this one sends a wave, and this one sends a wave. You see there, it's not in one dimension. If both of them reach a point in space doing the same, if both of them are peaks, that would be constructive. But if at some point, let's say here, and this one comes in and is like that, and this one goes and it's like this, you see this one is a minimum, this one is a maximum, that would be destructive interference here. So if the distance traveled by the first wave and the distance traveled by the second wave, if they differ by half a wavelength, assuming they're in phase to begin with, if they differ by half a wavelength, it will be destructive interference, or a multiple of an integer plus a half times an odd integer times half a wavelength, that will be destructive interference. And if it's an integer times a unit of a wavelength, then it would be a constructive interference. Okay. So I'm going to pause this in here, and I will see you next time when we do interference in time, not in space. That would be beats.